So as we mentioned previously, about half of all stars that we actually see are part of binaries. Now most of these, the stars are too close together and too far away for us to be able to actually see both stars. In other words, most binaries are not visual binaries. But that doesn't mean we can't figure out that there are actually two stars there. Instead of looking at the stars individually, what we do is we actually look at their spectrum. So these stars, where we can tell that there are two of them there based on their spectra, we call these spectrum or spectral binaries. Now, as the stars orbit around each other, we can look for them based on their Doppler shift. If one of them is coming towards us, the other one is going to be going away. So one will be blue shifted and the other will be red shifted. Eventually, they'll move perpendicular to our line of sight, which means they're not coming towards or away from us, which means we don't get any Doppler shift. Then they'll actually swap. So the one that used to be going away will be coming towards, and the one that used to be coming towards will be going away. And then again, they will go perpendicular, so we lose the Doppler shift. What this does is, as we look at the spectral features, looking at the spectrum, we'll see their spectral lines come together, and then separate, and then come together, and so on. Well, we can use the amount of shift to figure out how fast they're going, and we can look at the blue versus red shift to tell whether they're coming towards or away. So we can make these sorts of graphs. Known up and down, we're looking at the radial velocity. That's how fast it's coming towards or away from us. And then along the bottom, we're looking at time. So we can actually see how these stars are moving around each other. Well, as we do this, we can actually get all of the information that we need to figure out the mass of both stars. Looking at the star's radial velocity curve, we can figure out the mass of the ratio. And looking at the orbital period will give us the sum of the masses of each stars, which is everything we need to figure out the mass. So remember what we are doing. We are looking at a star, which from the Earth only looks as a single point of light. But because of very clever and careful measurements, not only can we tell that there are actually two stars, but we know how fast they're orbiting around each other and even the mass of each star. Now, some binaries are in just the right orientation so that as they orbit around each other, one star crosses in front of the other. These are known as eclipsing binaries, and we can actually tell that there are two stars there based on what we call the light curve. Okay, so these are examples of light curves. Up and down on the axis, we have the total brightness of the object, and then along as we go left to right, we're increasing in time. So what we're looking at is as the two stars are side by side, we see both of them, we have a maximum brightness. But as one star passes in front of the other, some of that starlight becomes blocked, so we see a drop, a dip, in the star's brightness until we see both stars again. Okay, so we look for these periodic dips in brightness that's going to reveal that these are actually two stars orbiting around each other. Now, using this, we can actually determine the temperature of both stars. Remember that a hotter star is going to be more luminous, giving off more light. So if it gets blocked, we're going to get a much deeper dip in the total brightness. Whichever star is cooler is going to be less luminous, so when it gets blocked, will lead to a smaller dip in the overall brightness. We can also use these to determine the size of the star. For example, in this middle row, we have a small star and a red giant. Because the big giant star is significantly larger than the small star, we're going to have a very long eclipse period. It's going to take a long time for the small star to move all the way through the width of the big star. So in that way, we can figure out relative sizes. We can figure out all sorts of great stuff by looking at eclipsing binaries. Here is our fourth lecture quiz question. What color of star is going to leave the main sequence first? And by leave the main sequence, I mean die. A, red, B, yellow, C, white, or D, blue. Go ahead and think about it, and we'll discuss in just a bit. Alright, so what color is going to leave the main sequence first? Well, the stars that have the shortest lives are the ones with the greatest mass. On the main sequence, the ones with the greatest mass are going to be the most luminous, but also the very hottest stars. And the very hottest color is blue. So, which color of star leaves the main sequence first? The answer is D, blue stars. So, first, the blue stars die out, then the white stars die out, then the yellow, then the orange, and then finally the red stars. Now, a star cluster is a cluster of stars. One of the things that I love in astronomy is that we often just call things what they are. We have a whole bunch of stars all together, that's a star cluster. These stars are close together in space, and they actually all formed at the same time from the same nebula. We'll talk more about stellar formation later. Well, as we look at star clusters, we can actually put them into two categories. What's pictured here on the right, this is what's known as an open cluster, also sometimes called a galactic cluster. In these, we generally have hundreds of relatively young stars. We can tell that these are relatively young because of the number of blue stars that are still in the cluster. Remember that blue stars die out first, so if there are still blue stars, then the cluster has to be relatively young. Now, these are generally found in the midplane, or what we refer to as the disk of the galaxy, which is why, again, they're also sometimes called galactic clusters. The other type of cluster is a globular cluster. This is what we have over here on the right. These contain hundreds of thousands to millions of stars that are very densely packed together. Now notice the overall color of this cluster. We have a lot of yellow, red, and orange. We don't really see blue or white. We do have this one blue star up here on the top, but I believe that's actually a foreground star that's not part of the cluster. So, the fact that we don't have any blue or white stars tells us that this has to be significantly older, and that's exactly what we find. Globular clusters tend to be very old. Generally, we find globular clusters out in the halo of the galaxy. So we have the disk of the galaxy, and then surrounding the disk is the halo. It's out in the halo that we find the globular clusters. Now we can look at the stars on the main sequence within a star cluster to actually help us figure out its age. Specifically, we look for what's known as the main sequence turnoff point. This is the point along the main sequence where the stars are beginning to die. And when a star begins to die, it then leaves the main sequence. So we can look for where the stars are leaving the main sequence, and that helps us to determine the age. Remember, blue stars have short lives, red stars have long lives. So as we go down the main sequence, we're actually looking at different ages of stars. So depending on exactly where that main sequence turnoff point is, will tell us about the age of that cluster. So, for example, here we have the cluster NGC 2264. This weird sounding number is actually its catalog number. NGC is the catalog, and then this is number 2264. As we look at the stars along the main sequence, we actually have blue stars all the way up to the top of the main sequence. In other words, this is so young, no stars have yet died, so it has to be less than around 4 million years old, which when we're dealing with stars is very, very young. Here's another cluster. This is the Pleiades. You can actually see it with your naked eye in the wintertime. In this case, notice that some of the blue stars have died out, but we still have all of our white stars and yellow and so on. Okay, so the blue stars are gone, but we still have white. That means that it's going to be older, maybe 10, 15 million years old. So the older the cluster is, the farther down along the main sequence the turnoff point is going to be. So here we have a whole bunch of different clusters. So the black line over on the left, you can see the diagonal it's making. This is the main sequence. All of this stuff happening over here to the right, this is where stars go as they begin to die. We'll talk more about that stuff when we get to stellar evolution. How does it stars change as they age? So looking at this, going all the way to the top, we've got NGC 2362. Then the next one is H plus Chi Persei. Then here we've got the Pleiades and M41. And then all the way down here, we have M67. So we look at the main sequence turnoff point, and that's going to give us an idea of the age of the cluster. So here is our fifth lecture quiz question. Which of these clusters is going to be the very oldest? NGC 2362 right here, the Pleiades there, NGC 752 through here, or M67 right here. Go ahead and think about it, and we'll discuss in just a bit. Alright, so which cluster is the very oldest? Looking at NGC 2362, it goes all the way up along the main sequence, meaning it has to be super, super young. The Pleiades has a main sequence turnoff point lower, so it's older than NGC 2362, but its turnoff point is still within the blue region, so it's still going to be pretty young. NGC 752 is way down the line along the main sequence, but it's not the very lowest one. Its turnoff point is somewhere in the middle of the white stars. But M67, of all of these, has the turnoff point that is the very, very lowest. And because it's the farthest down the main sequence, this is going to be the very oldest cluster. So M67, answer D, is the correct one.